All right, this is chapter 8, number 47. This is the one, there's a neutron star, and it tells us that this neutron star has a radius of 10 kilometers. And you'll see I converted that to meters. Just a little dimensional analysis. The time it takes for one rotation is 0.04 seconds, so it spins very quickly. It's because it used to be a full-size star, and rotational momentum is conserved, and it had a large radius, and now its radius is decreased so much that it's spinning very quickly. And its radius too, so what they're saying is it's going backwards from what happens in nature. Now they're going out to a full-size star, and its radius too, which is 1.4 times 10 to the 8th and meters, and they want to know the time that it's going to take to spin one time once it does this. So the first thing I did is I did omega initial, which is, it told us that it was 1 rev over 0.040 seconds. I did the dimensional analysis and I got to this. I don't know why I left it in like that. I usually get a number, but maybe there's a reason for that. We'll see. And then omega final is 1 rev in over T2. So we don't know what T2 is. We don't know that time. And so I just get 2 pi radians over T2. So I kind of got stuck and I stopped there. And so anyways, here's a new thing that we haven't really talked about yet, unless you've read the book, which you should have. This is rotational momentum. It's conserved, and it's L, and it's equal to I, which is moment of inertia, times omega, which is angular speed. So this rotational momentum, you think of it like in class when we put somebody on that spinning wheel and they put the weights in their hands and their hands were out wide, they had rotational momentum. And then they took their hands and they pulled them in to their body and then they sped up. Well, what that was is that was showing us that rotational momentum is conserved. And so you, because their radius was smaller, their speed had to increase. So for this object, it is a solid sphere. It's a star. So for this object, I is equal to 2/5 mr squared. So for the first one, we get L equals I times omega, and it's 2 pi radians over T1, and that's just the first time. And then I did the same thing for the second time period when the planet is a different radius. So you'll see this is at the beginning and this is at the end when it gets bigger. Since rotational momentum is conserved, what I did is I set those two equations equal to each other. So you'll see that I took this one and made it equal to that one. Since there is no drag in space, this is actually not just theoretical, this is truly what happens. So we have this equation. Now you'll notice that the 2/5 mr squared and the 2/5 mr squared and the 2 pi radians and the 2 pi radians, that's the same on both sides. The only thing that's different really is you have R1 on this side, R2 on this side, T1 on this side, T2 on that side. So this big nasty equation kind of simplifies down to R1 squared over T1 equals R2 squared over T2. So it gets very simple, and then what I did is I manipulated it and get T2 by itself, and then really truly all I did is plug in the numbers. And when I plug in the numbers, I get a T2 of 7.84 times 10 to the 6 seconds. That doesn't make much sense to us, so I'm going to get rid of seconds. And so I have those seconds, and I did a bunch of dimensional analysis, and I keep going, get to days, and I get 90.7 days as my answer. And that's the time it takes for one rotation of this neutron star once it expands to its second radius.